Okay, this video is going to be explaining the basic concept of a counterboring fixture designed to use end mills for counterboring instead of counterbore bits. So I'm going to demonstrate it, and then I'm going to explain it in as much detail as I can. This was taught to me. If I get permission to post this in the forum, I'm going to give credit to Tom Watson, who's a retired knife maker who frequents the Steel Dust Junkies subforum here in the USN. Really nice guy who, for no reason other than I guess the kindness of his heart, decided to teach me how to do this by sending me detailed pictures and descriptions in emails. So that was really cool of him. I appreciate that, Tom, if you run by this video, which you will, because I'm going to ask you for permission to post it. I don't know if he made it up, but he's the one who taught me, so therefore he gets the credit. For demonstration purposes, we'll be using the universal testing color of pink, and this is a piece of G10. This is going to be a one-take video, because even if I did have editing software, my computer is much too underpowered to run it. I might provide a little bit of commentary while I do this. That way I don't forget anything while I am explaining it. This top piece of this fixture, as you can see, can move around. At this point, we're going to tighten our X and Y axis. We don't want those to move at all. And now that we have this shaft inside the fixture, that is now fixed in place, we're going to go ahead and tighten down this top plate. Don't worry, all this will be explained. And if I don't explain it in the video, I can explain it in the comments. I'm sure a lot of guys on this forum already use this, but for anybody who doesn't already use it, this is probably going to be helpful because it's a lot easier to explain on video. Using 1/4 inch G10 for this fixture. You could use obviously aluminum or steel if you want. G10 is just easy to work with, but I wouldn't go any thinner than a 1/4 inch because rigidity is the key in machining, and this is no exception. So now we have this top plate, the top part of the fixture, locked in place. And we have it positioned perfectly because we have this shaft in it right there. So now we can raise the shaft up, and we're going to put what I believe, correct me if I'm wrong, is called a boss. In other words, a protruding feature right here. That right there, give a little tap down. Yes, that right there is what's going to hold our workpiece in place. So we'll just pop that workpiece in there, which has a pre-drilled 1/4 inch hole. This is a 1/4 inch brass rod that I cut off and put in there. You can find a brass rod at just about any hardware store. Any reputable one, anyways. This right here is just another piece of G10 that I'm using to clamp this down. Put these, whoops. I'm gonna take video for you. These are 1/4 inch 20 screws, which also you can find at just about any hardware store. In retrospect, I would advise that you use a more rigid piece for this clamping right here because, oh, you know, run into a problem. Yeah, that's something you don't want to run into right there. These screws, or these bolts, are too long, so they're actually raising the top plate off the bottom plate. You don't want that. So we're just going to rely on the flatness of this fixture to hold this this piece in place here. Make sure your screws are short enough. They have to be just long enough to where you can actually fit your workpiece underneath there, and short enough to where they don't raise the top plate off the bottom plate. And we might have thrown everything off of zero there, but we'll see about that. Alright, now I'm going to take out this feature right here and put in the end mill that I'm going to be using to counterbore. Hopefully everything will stay zeroed. I'm using the term zeroed quite loosely. This, by the way, is a 1/4 inch by 3/8 counterbore pilot that I pulled out of a set that I have. And we're going to pop in to our 3/8 collet, a 3/8 carbide end mill from Lakeshore Carbide, which a lot of guys on here use. I don't remember who turned me on to them, but I'm glad because they're decently priced. American made, solid carbide with a good coating on there. Come on. Alright, we got that snug. In this mill that I'm using is the Grizzly G8689, which is their cheapest, smallest mill. And there is a micro down feed, but in this case we're not going to use that. We're just going to eyeball it by using the depth ruler on the side there. We'll just notate where it is and go down by about 1/16 of an inch. I mean, you can get more accurate than that, obviously. Alright, we can't even see what we're doing here. Let me see if I can move this camera. You can actually see what's going on. This poor lighting. Okay, well basically we have the end mill should be in the right spot because we basically switched out that pilot in the 3/8 collet and put in a 3/8 shank end mill in there. So everything should be zeroed in the same place. Now let me just adjust the camera. Yeah, this is going to be a crappy video, but what can I say? It's not like this is a studio, this is a little cheap shop. There we go. Notepad. Alright. Like I said, keep your X and Y axis locked. And we're going to take it down about 1/16 of an inch. What's the deal? Oh, my depth limiter's on. There we go. Hold that flat. Where are we going down? What's holding us? Oh. Stupid tension bar on here. Oh well, that was deep enough for demonstration purposes. There we go, we have a counterbore. Not as deep as I wanted to go. Matter of fact, let's try that again. The problem I'm having is this stupid tension spring on here doesn't allow the end mills. It'll go down to right here, and it doesn't even get really close to the table. I don't know what they expect you to do. I guess they expected you to always be using a really tall milling vise and tall. I mean, we're talking that's about 4 inches off the table, and the end mill is not reaching it. It's pretty pathetic. Stupid design, in my opinion. But whatever. Yeah, we're gonna loosen that end mill in there and drop it down a little bit so we can actually counterbore this to a decent depth, so we can see if we actually got an effective counterbore. Shank is not super long on this, but at this thickness or this diameter it'll be rigid enough with me dropping it down that far, where it shouldn't throw it off a zero bad. Of course, when you do this, you're gonna really want, if you're doing this for a expensive piece of titanium, you're going to want to get this clamping system squared away, because if you don't and your piece goes up or down, your counterbore is going to be off and your knife is going to be off center. But like I said, for demonstration purposes, this should be just fine. I'll just hold it flat with my hand, and these screws right here will keep it from rotating, which will be nice. So let's pop it back on that boss there, bring it down, turn it on. You can see I'm very safe because I have my fingers really close to the cutter right there. That's what all good machinists do. Alright, let's take it down a little bit. Let's take it down further than that. Alright, I'm going to use an Emerson pivot to test it out. See if our counterbore's straight. Ooh, camera. Alright, yeah. Fits in there perfectly. Perfect counterbore. And once you have it set up, you could basically take, any number of knives. As long as you have everything tightened down, you should be able to repeat this process over and over again. So obviously you don't want to do this setup between every knife you do, but set it up the day you decide to do your counterboring, and you could do 100 knives this way and you'd be just fine. I did it with titanium already, and it just glides through there, no problem. See that? Fits in there perfect. We're talking tolerances in the 10,000ths probably. Maybe not. I don't know. So let's explain this in more detail. If you want to counterbore wood, aluminum, mild steel, maybe carbon fiber, you're just fine using a counterbore like this. A fixed pilot counterbore, high-speed steel would be fine for most of those materials. They also have the interchangeable pilot counterbore. You can see the hole right there for putting the interchangeable pilot. But if you're going to do titanium, these are not good at all. Not only will they dull fairly quickly, I've heard a lot of other machinists, or I should say knife makers / machinists, have used counterbores and they dull quite quickly. And if you get them too hot, which is pretty easy to do with titanium, even if you're going slow, titanium just doesn't conduct well like aluminum. You can melt the tips of your cutters, like right there, in high-speed steel. So just not good for a titanium. And if you want to buy a carbide counterbore, be my guest. that may last a little bit longer, but it's going to cost you, I would say, 3 or 4 times more than your comparable end mill like this one right here. And honestly, I don't even think it gets as good of a counterbore. So I think this method is ingenious, and that's why I'm going to use it from now on. So I'm going to unscrew this right here. If I didn't already mention this video, since we're 15 minutes in, I don't even remember what I did at the beginning. This method is for mills. As far as I know, you can't do this with a drill press because you need to have a collet system. You cannot use a 3-jaw drill press chuck like this one, because every time you tighten that down, because it has 3 fairly loose jaws in there, it's going to move the position of your cutter over by at least a couple thousandths in any one of those 3 axes right there. So you're not going to get a good counterbore that way. You might be able to pull it off, but it's just not going to be repeatable like this system. So here's the basics of this right here. Like I said, this is only a concept. There's other ways I'm sure you can do this, but this is how I ended up making my fixture after being instructed by Tom. He was just, for demonstration purposes, was using vice grips to tighten down his top piece of his fixture, but he said you could just tap the bottom piece with some bolts, and that's what I went ahead and did with this 1/4" G10. Alright, let's go ahead and unscrew already. There we go. The bottom piece I have tapped for these 1/4" 20 screws, which you can find at just about any hardware store in the US. But the top piece, the corresponding holes that I drilled are oversized, because you want this piece to be able to move around on top, because the bottom piece is going to be viced in, but the top piece you need to be able to move over on the X and Y by a couple of millimeters to correspond with where the shaft that I have in the collet is positioning it. The shafts that I use, and this is going to be for any knife with a 1/4" pivot, which I'm going to be using Alpha Knife Supply for the folder I'm working on, and they have a 1/4" pivot, so that's what I made the fixture for. And I don't have a lathe, so I wasn't able to just turn bars at the diameter that I needed, so I used these Counterbore pilots that I had in a set, which really turned out to be handy. I'll probably cut these down to where this little tapered area is not there, but I've already used these at this length, and they seem to be rigid enough. The one I used for the video is this. It's got the 3/8" pilot and the 1/4" shank or shaft. So this right here went into the 3/8 collet, which the 3/8 end mill is sitting in now. A collet. I'll show you what a collet looks like. If you don't already know, you will know if you have a mill. But what the heck? I'll just show a collet. That's a 3-jaw collet, and that right there is gonna hold your piece in pretty much the exact same position and much more rigidly than a 3-jaw chuck will. Because, I mean, it only moves by a few thousandths or hundreds or 10 thousandths when you tighten it. So that's a 1/2" right there. So if you had a 1/2", if you had a cutter with a 1/2" shank, then you could use that. And so any collet that I use that it has a size that corresponds with these pilot heads, it'll work with this fixture because all the shanks here are 1/4". And you can buy these on like MSC Direct or Enco, or any kind of big box or not big box, but big machine supply website, instead of having to have someone turn them on a lathe. So, like I said, you put your pilot, big side up, if you will, into the collet. You lower the shaft down into the hole where the boss will go eventually. Like the boss will be removed, that little brass piece right there. I just popped that out right there. You lower this into that hole. Then you tighten these 4 screws so the top piece is fixed in place just like the bottom piece. And you keep the X and Y axis locked. Obviously you don't want anything to move around. Then you take this piece out, put in your end mill into the collet, and it should be zeroed to the same position, X and Y, that your original pilot piece was. That way, when you come down to counterbore your piece, which is fixed in place, you put the boss in after you take the shaft out. It'll counterbore concentrically. I don't know if that's the right term, but it'll be straight. So yeah, that's the basic concept. I have this 1, 2, 3 block underneath there to basically raise it up to where when I tighten my vise, it's only clamping down on the bottom piece, because like I said, you want the top piece to be able to move around. So I mean, depending on which milling vise you use, you can use, that's not a parallel, I don't know what you would call that, but just basically something to raise it up. So you'll have to find the right pieces for that. But in my case, the 1, 2, 3 block worked perfectly. What am I forgetting? Yeah, like I said, you'll want to shorten your screws there to the right length. But that's the basic concept. Thanks for watching this incredibly long, tacky, and boring video.